Alright, let's have a look at this one. So, again, this one doesn't look like a radical because it has a rational exponent. We have a 3, and well, let's see. Of course, from laws of exponents, recall that we can rewrite some a to the m over n. This is either the nth root of a to the m or the nth root of a and then the whole thing to the m power. And I'm going to do the latter one, right? The one with the m outside. So that's the integral from 0 to 1, the square root of x squared plus 1, quantity cubed. And well, from there, let's figure out the substitution. Number 1. Do we have a difference of squares or do we have a sum of squares? Sum of squares. So those quantities, in this case, u equals x and a equals 1, those two quantities will be the ones that will label the triangle. So let's label the triangle theta. And well, again, I usually set the opposite to be the variable and the constant term to be the adjacent. And if you do the Pythagorean theorem to find the hypotenuse, you will get 1 squared plus x squared, which is the square root of 1 squared, or rather simply x squared plus 1. Alright? So let's go ahead and do the substitution. So the first part of the substitution is radical over constant or radical over x, the simplest of them. Which one is the simplest one?
Over 1.
So the over 1, radical square root of x squared plus 1 over 1. And what is that trigonometric function that relates those two quantities? Which one is it? Secant. Oh, not the theta. Well, so score for the first one. Well, let me just simplify. Square root of x squared plus 1. If we had a different number in the denominator, we would multiply both sides, which is technically what I'm doing. But I mean, multiplying by 1, it's same. Okay, so that's the first part. The second substitution. Okay, so we need to get a substitution for x in order to figure out the dx, the differential part. So we have two options to relate. X over 1 or x over radical. Which of those two is the simpler one? X over 1. And what is that trigonometric identity that relates opposite over adjacent? Tangent. Alright, so x equals to tangent. And from there, differentiate both sides, find the differential. That's a secant. Alright, so we have everything we need. So let's replace this radical part right here with secant. That is the integral, and I'm going to skip the limits. I didn't change the limits to the world of theta because it would have been a big mess to do that. In the meantime, I'm just going to stop writing the limits and focus on everything else. Well, so we have secant quantity cubed, and in the numerator for the x, we're going to have secant squared theta d theta, which will be really nice because this cubed over, this square over this cubed is going to leave us with 1 power of secant. And well, we cannot just integrate secant while it's in the denominator, but the good thing is using identities, that's integrating cosine, which is really nice, very short. So the integral of cosine is its sine. I'm going to stop writing the plus c, and I'm going to go back to the original terms of x. Okay, we got a sine. So sine in terms of x, which is opposite over hypotenuse, that is x over the square root of x squared plus 1. evaluated from 0 to 1. So that's where I will incorporate back those limits of integration, because we're back to the world of x. And then from here, what is this? Fundamental theorem of calculus. So that's 1 over the square root of 1 squared plus 1 minus 0 over the square root of 0 squared plus 1. Well, so that's simply 1 over the square root of 2. The second term gets zeroed out. And well, in this case, you might want to rationalize the denominator to get square root of 2 over 2. Okay. Yes. All right. So